Okay, ask someone how to get it. I don't know what the problem is, but you should be able to print out your code.
Okay. You want me to turn it down with that?
No, turn it in later with the code.
I put don't record breaks on this setting.
Okay.
Thanks.
Okay, we ready to go? Looks like we're on the air. Okay, thank you. All right, homework 1 is due today. Remember, you should have your code, your output. The answers should be filled in on the cover sheet, and then everything should be clipped together, stapled together on the upper left-hand corner. And if you haven't handed it in yet and you're late, that's okay. Don't worry about it. In this case, it doesn't matter. So I'll take them when I get them. And also, I received today an email from a student who gave some detailed directions on how to download and use BASIC. I think the directions are better than they were before. So if anybody wants to see them for the future, just send me an email asking for QBasic, and I will send this file back to you. Any other questions? Yeah.
I had a problem with printing from the output screen. It wouldn't allow me to. Is there some trick or something that somebody knows?
Yeah, can anybody answer that?
When you run your output, it was
So, does that answer it? Okay, this. Okay, so even though I couldn't hear it, I assume you got your answer right or not right.
Yeah, that happened to me too, so I didn't give you a printout of it. It's not all right?
No, submit a printout.
Okay.
Okay. Let's see. Do you have any, yeah. All right, are there any questions? Remember, if you want the latest version of the basic directions, email me. And the last thing we were working on was homework 0. And I had done some of it, so let me review some and do number 2. And let's make this due 3 weeks from today. So that should be plenty of time, especially since almost all of it is being done right here in class. So what we're looking at is the second case where the density function is given by the following formula. It's 0 when t is negative, and it's lambda e to the minus lambda t when t is not negative. And one of the questions is to draw the graph of that thing. And so the graph would look like this. So here's t, and here is the density function of t. Here's 0. And what I asked you to do is, in the case in which you have to draw a graph, do numerical work, I want you to take lambda to be 2. So if you were to draw this graph, it's 0 when t is negative. Then there's a discontinuity, and it jumps to the value lambda, which in our case is 2. And then if you plot it, you should get something that looks like roughly like that. Of course, you're supposed to not just sketch it, you're supposed to plot it. And so when you plot it, the best way to do that, show me what you're doing, is something like this. You would write the values of t here and the values of f of t here. And then you pick values of t, like, for example, minus 0.1. And at that value, the function would be 0. And then you'd pick 0, and at that value it would be 2. And then you would pick, say, 0.1. And at 0.1, it would be 2 times e to the minus 2 times 0.1, whatever that number turns out to be. So you have these values of t and the values of the f of t, and then you would plot them here like that. So for each one you would plot the numerical value which you get from a calculator, or you could write a program in BASIC and run this in an instant, and then you connect the dots. And I can really see the dots. Remember, that's only for your own guidance, because what you're doing here is you're plotting this function for all values of t, not just the values of t that you calculate. Okay, so that's what the density function should look like. And then it asks you to calculate some stuff. So one of the things it asks you to calculate is the expected value, which, remember, is the mathematical model or idealization of the notion of average, which we'll see later on in the course. Remember that now this is just a arithmetic or calculus exercise. And the definition is it's the integral from minus to plus infinity of t times the density function evaluated at t dt. So now you plug in the particular f for this particular case. So that would give you the integral of t. Now, this function is 0 when t is negative. So since t is running between minus and plus infinity, I know that between minus infinity and 0, the f is replaced by 0, which means that the integral is going to be 0 for that part. So I can start my lower limit at 0 and run to infinity, because in that range, the function is given by lambda e to the minus lambda t. And then you integrate this. However you do it. You do it the old freshman calculus way, you integrate by parts. But it doesn't matter to me what technique you use or whether you look it up in a book, as long as you state where you got it from. And when you get done with all of that, the answer will turn out to be 1 over lambda. So I'm just going to write here by parts. So if you want to work that out, that's fine. If not, that's background material. I don't care whether you're good at integration, as long as you're good enough to get the answers we need in this course. Okay, so the answer is 1 over lambda. And then it asks you to calculate the expected value of the square of x, which is the second moment. And this will have applications. As an application, it describes the amount of variability in a random variable. And the formula is the same as that, except instead of t, you have t squared. So that would be t squared, density function evaluated at t dt. By the same argument, that would be the integral from 0 to infinity of now t squared lambda e to the minus lambda t dt. And again, if you integrate by parts, you will get 2 over lambda squared. Right now this doesn't mean anything, but later on in the course it should have some significance. Okay, so I did that last time. Then it asks you to calculate the distribution function. So the distribution function, the convention is that's called capital F. And by definition, it's the area under little f between minus infinity and t. So this is the integral from minus infinity to t of little f. Except now, I can't call the argument here t, because I'm using t as the upper limit here, or as the argument here. So I call it anything other than t, I tend to use u. So it would be density function at u du. Now, when t is negative, obviously this is 0 because this function is 0. So if I evaluate this integral, I'll find out that it's 0 when t is negative. When t is not negative, this would be the integral from 0 to t of lambda e to the minus lambda u du. Now this is a simple integral, because remember that the exponential is the function whose derivative and integral are equal, or whose derivative in itself are equal. So what that means is this is a really simple one. When you integrate this and plug in the limit, it'll turn out that the answer is 1 minus e to the minus lambda t. So that's for t greater than or equal to 0. Now you're supposed to draw the graph of that, because I didn't leave enough room here, so let me erase this. This is 0. Here's t. Here is the distribution function evaluated at t. Capital F x of t. And of course, when t is negative, it's 0. And you should indicate that on your graphs. Don't just ignore the 0 part. It's an important part of the function. And then, when t is not negative, you're now drawing the graph of this, which will look something like that. It'll be asymptotic to 1. And of course, since integral means area, what that means is that the height of the graph at this point, at any point, that height is equal to the area in the graph above it to the left of that point. So this height is that area. And similarly, this height, the height of this graph, is a derivative of this graph. So you have to plot this the same way you plot that. I did that last time. So any questions about that? Now later on in the course, you don't have to plot these things by hand, but for this exercise, I'm asking you to do it by hand, and everybody should use the same scale, the same graph paper, which you download from the website. Then it asks you to calculate capital F. Oh, wait a minute, we just did capital F. It asks you to calculate, and this isn't on the version that's on the website, but it will be. So it asks you to calculate the integral between a and b of the density function. So in this particular case, it tells you that a is equal to, 0.25, and b is equal to 1.35. Is that correct? Are those the values I said? Okay, and this is numerical, so now you want to plug in the numerical values of f. So that's going to be, since lambda is 2, that's 2e to the minus 2t dt. And now you integrate that. And basically there's two ways to do it, or there's multiple ways to do it. One way is to recognize that since you already know what the distribution function is, because you calculated it in the previous part, that means that I could calculate the distribution function evaluated at the upper limit and subtract the distribution function evaluated at the lower limit, which means you don't have to do any more integration because you already integrated, and then you get some answer. I don't know what it is, but it's just a number. Another way to do it is to do it with a calculator. That is, you have something like a TI-83 or 89. You tell the calculator the integrand, the variable of integration, so it knows what it's integrating over, and you tell it the lower limit, the upper limit, and you press the button, and then some number comes out. Of course, it should be exactly the same number. And also, you could just integrate it directly without using this. Of course, you're going to get the same result, because when you integrate this, what you're going to get is, in fact, the formula that you have right here, except that instead of lambda, it's going to have 2. And then you're going to plug in that value and that value and subtract them. Of course, they're all going to give you the same answer. Okay, so I don't know what that answer is, but it doesn't matter. It's some number. Then it asks you to calculate g of t, and that's where things might be a little bit different, or more difficult than anything you've seen before. So here is the definition of g of t, and it's called the convolution. And the definition is, you take one of the functions, actually you can take the convolution of different functions, but I'm using the same function twice, which is the usual application, but not necessary. So I take the density function evaluated at u, multiplied by the second function, which in this case is the same function, evaluated at t minus u, and then I multiply by du and integrate between minus and plus infinity. So what this says is, take these functions and multiply them together, and that gives me a new function, and then whatever that new function is, find its integral between minus and plus infinity. And the difficulty is, in this case, is that the way I've defined these functions is that these functions have different branches. So as the u moves between minus and plus infinity, the f could be jumped from one branch to the other branch. And same thing here. But this one is more difficult to understand than this one because where the jump occurs depends not just on the value of u, but it depends on the value of t minus u. If t minus u is negative, then f is 0. And if t minus u is not negative, then f is given by this formula with t replaced by t minus u. So that's what we have to evaluate for this particular case. Actually, you have to evaluate it for two cases. In case number 1 is in some sense easier, but in some sense harder. It's easier because the functions that fit in case number 1 are simpler functions. They're only 0 or 1. But it's harder because in case number 1, little f has 3 branches, and in case number 2, it only has 2 branches. Okay, so let me do this for case number 2. Okay, so I want to calculate this integral minus to plus infinity of density function at u, density function at t minus u, du. And now I'm going to plug in the functions. So the first thing I'm going to do is recognize that when u is negative, because it goes from minus to plus infinity, little f of u is 0. Because to get this thing here, I go back to the definition here, except that here it's defined in terms of t, there it's defined in terms of u. So that would mean that the function that fits in there is this with t replaced by u. So that would be a u, that would be a u, that would be a u. Okay, so that means that this thing is 0 as long as u lies between minus infinity and 0. So right away, I can rewrite that as the integral from 0 to infinity of lambda e to the minus lambda u, which is the value of this function when u is not negative, times that. I'll write that as fx of t minus u. And now I have to evaluate that. And so the trick is, what do I put in here for this? So the first thing to recognize is that suppose that the t is negative. Because remember, this is a function of t for all t. So if t is negative, what that means is that since u is a positive number, because u is ranging from 0 to infinity, that means that t minus u will also be a negative number. So since t minus u is negative, that means that little f of that is 0, and that means that whenever t is negative, the integrand will be 0, so the answer is 0. So it's 0 if t is negative. So we have to worry about the case where t is not negative. So suppose t is a number like 7.2. This thing says that u starts at 0. So initially, when u is 0, that's going to be 7.2 minus 0. And then as u gets larger, because u is moving from 0 to infinity, this becomes 7.2 minus u, gets smaller and smaller. And when u reaches the value 7.2, the argument becomes 0, and the function jumps from one branch to the other branch. So as long as u is less than t, this function is given by this formula, except that t is replaced by t minus u. And when u exceeds t, the formula is given by 0, because I jump from this branch to this branch. So that means that this integral is going to become the following. So I'm going to say, suppose that t is greater than or equal to 0. Then I'm going to have the integral from 0, lambda e to the minus lambda u. Now, as long as u is less than t, that function is going to be given by lambda e to the minus lambda times t minus u. I still have my du. But this is what the function equals only when u is less than t. When u reaches t, that argument becomes negative, which means that function right there is replaced by 0. So in effect, what that does is that stops the integration at t. It cuts off at the upper limit. And now I have an ordinary integral that I have to evaluate. Okay, so the whole thing here is understanding how the integrand changes its formula as u varies between minus and plus infinity. Now, this may look complicated at the moment, but this is in fact very easy to evaluate. Because all I have to do is rewrite this, and let's see, I have the integral from 0 to t. Then I have a lambda. Then I have e to the minus lambda u. Then I have a lambda. Now, this e to the minus lambda t times t minus u can be written as e to the minus lambda t times e to the plus lambda u. And I still have my du. So all I did in going from here to here was to represent this exponential as this product, break the exponent into two pieces. Okay, now you can see why it's important to keep the t and the u straight. Because when I'm over here, I can see that e to the minus lambda u cancels with e to the plus lambda u. The product is 1. And what's left is lambda, lambda, e to the minus lambda t. None of those things have u in them. So therefore, the integrand is constant with respect to u. So that means, running out of space again, that means that this integral becomes lambda squared, those are the two lambdas, e to the minus lambda t, integral 0 to t du. Everything with u in it canceled out. Well, the integral of du from 0 to t is simply t, so therefore this answer is lambda squared t e to the minus lambda t. So that's the answer. Lambda squared t e to the minus lambda t for t greater than or equal to 0. Now it asks me to draw the graph of that thing. Okay, so that's simple enough. Same thing you did in the other cases. So here are the axes. So here's g of t, and here's t. Okay. Remember, this is a function of t now. The u integrated out, and when I got it all done, I have a function of t. Okay, this function is 0 when t is negative. And then it's this curve right here. And of course, I asked you to, when you do this numerically, I asked you to plug in a numerical value for lambda, which I said was supposed to be 2. So this is the function 4t e to the minus 2t. And if you plot that, you'll see it looks something like this. Okay, so the graph of that part is 4t e to the minus 2t. And you plot that the same way you plotted this. And that's it. Okay, so this may be different from what you learned in calculus, but you can see this is the essence of calculus. I'm just following the rules here, and the actual requirements for the integration are pretty simple. The tricks are pretty simple. All you have to do is understand what integral means and what function means. And after that, a computer could do it. In fact, a computer can do it. I mean, I could go to more powerful software like Maple, I suppose, and I could tell the program that what the definition of these functions is, what the limits are, and then it would simply do the arithmetic for me. Question?
So what if this t is equal to u?
If t is equal to, well, remember u is the variable. When t equals u, that's f of 0. Okay, now f of 0, according to its definition, is lambda. Okay? I mean, I'm not sure what the problem is. One thing I should emphasize here, maybe this is your question. Whenever I have an ordinary Riemann integral, the value of the integral at any specific point is 0. Not the value of the integrand, but the value of the integral. Because remember that what this integral represents is taking strips of infinitesimal width and finding the area under that strip and then adding those areas up and then taking the limit as the width of the strip goes to 0. So if I had an integral evaluated from 0 to 0, let's say, or from A to A, let's say, then since the width of the strip, since I'm integrating only over a point, the area enclosed above a point is 0. So it doesn't make any difference what the value of the integrand is at any specific point. In fact, that's going to turn out to be one of the major things that people tend to lose sight of. I don't understand why. I mean, this is like the main point of the course. I see this over and over again. I always ask this question on the final exam, and half the class always misses it. So let's make this an exception, right? No one's going to miss it. Because later on in the course, it'll turn out that the density function is something, is a function whose areas are probabilities. So if I give you a density function, doesn't matter what it is, and I ask you for the probability that a random variable with this density function has a specific value, 6, doesn't make any difference what it is, then that would be the integral from, in this case, 6 to 6. Well, the integral from A to A of any integral is always 0. So the probability then, which is there for that area, is 0. Now, right now you can't, this doesn't make sense because you don't know what probability and density function means. But when you, later on in the course, when you get to where you would answer that question, the way you would calculate the probability is to calculate the integral, and if you're integrating over a single point, it doesn't matter what the integrand is, the integral over a single point is 0. So the probability is 0. People don't seem to be able to digest the fact that a random variable that can take a value will have a probability of taking that value. And that actually turns out to be one of the main concepts of the course. In the simple discrete case, if a random variable has probability 0, that means it never occurs. But in the general case, a random variable can have a value 0, or that is probability of a random variable taking a specific value can be 0, without implying that that value is impossible. Okay, so we'll see that later in the course. But I think that's the answer to your question here. It doesn't make any difference what the integrand is at any specific point. All that matters is over a range of points. Okay, anything else on this? So now what we want to do is we want to do this for case number 1. So of course I don't want to do that, because if I do that I've done everything for you. So just let me do half of everything for you. Well, since I've done all this will be like 99%. Okay, so now we're going to take case number 1. And I want to evaluate G of t. Okay, now in case number 1, let me rewrite what the f is. So I think I'll do that here. So case number 1, the f is equal to 0, the little f is equal to 0 if t is negative. It's equal to 1 if t lies between 0 and 1. And it's equal to 0 if t is greater than 1. And we want to evaluate the integral between minus and plus infinity of little f evaluated at u times little f evaluated at t minus u du. So I want to simplify this based on this particular definition, just like I simplified this based on the definition for number 2. And the first thing to see here, the step I'm going to make, is to say, well, when u varies between minus and plus infinity, f of u, according to this definition, because remember f of u is just this with t replaced by u, this is 1 when u lies between 0 and 1, and it's 0 everywhere else. So that means I can immediately rewrite this as the integral from 0 to 1 of 1 times f of t minus u du. And now all I have to do is worry about what little f here is. Now, The value that fits in here is either 0 or 1, depending on whether t minus u lies between 0 and 1 or not. If t minus u lies between 0 and 1, that thing is 1. If t minus u does not lie between 0 and 1, that thing is 0. So that means that the value of this integral, which is the area under this curve, is going to depend on t. So different values of t are going to give you different values of the function that fits in here. But once you get that set up, you'll realize that all this amounts to is a rectangle. And so when you actually evaluate the integral, the area under a rectangle is simple. All you have to know is what rectangle it is. So that's the only hint I want to give you at the moment, except to say that there are really two ways to do it. One way is to make believe that you don't know anything, don't know any calculus, and simply follow the rule. This says, find the area under this curve, because you can ignore the 1 now. Find the area under this curve, integral, 0 to 1, of f of t minus u du, where f is given by this formula. So you don't have to know any calculus to do that, because as soon as you know that integral means area, then if you follow the rules for a function, all it says is, for different values of t, find the area under this curve between 0 and 1. But to do that, you have to sort of understand what you're doing. There's another way to do it where you don't have to understand what you're doing, you just use the rules of calculus, and that is you make a substitution. And when you make a substitution, everything is mechanical, and the answer comes right out. Of course, that removes some of the intuition from it, so we'll leave that till later. But for now, that's all I want to tell you. And that's it. That's the homework problem. If you understand this, then you're okay as far as the mathematical level goes for the rest of the course. Let's see, there was one other piece here. No, I guess I have everything. Right? Is there anything I skipped here? Okay, so we're done with homework 0. So let's make it due 3 weeks from today, which, you should be able to do it now in an hour. Because it won't be true. I know a lot of people are going to have trouble with this, because that always happens. But if you do, that's your fault. There's nothing to it. So no questions? Okay, so now we're back to probability. So according to my bookmark here, we had discussed Chapter 1, Axioms of Probability, and I had shown that there's one special case that's simple, the simplest case, of what's called a discrete random variable that takes a finite number of possible values and all of them are equally likely, which means that if there are n possible values, then each one has probability 1 over n. And that means that if I want to calculate the probability of any event, all I have to do is take a ratio. And the numerator is the number of points in the sample space that correspond to the event. The denominator is the total number of points in the sample space. The ratio is the probability. And so I proved that before we started talking about these homeworks, and I gave examples using the dice problem. And then I said that with the dice problem, it was easy because you could simply count the points in the sample space because there's only 36 points. But in general, there could be zillions of points, so even though in principle you're just counting, in practice it's not practical to count them just by writing them down and counting. What you have to do is you have to use some systematic mathematical way of counting, and that's called combinatorial methods, and that's in Chapter 2. And a lot of the stuff in Chapter 2 then really has nothing to do with probability. Once you recognize that you're just simply calculating this ratio and counting, then the probability part goes away, and it's just a matter of calculating numerator and denominator. And these methods, these combinatorial arguments, are the basis for the course in discrete math. So if you've taken discrete math, what I'm talking about now should be a review. In fact, the stuff that I'm going to talk about now, I learned it first when I was in high school. I didn't understand it, but it was in principle simple enough so you could teach it in high school. So if you've had discrete math, you already know this stuff, and if you haven't had discrete math, then when you take discrete math, it'll be easier, at least at that part of the course. The courses intersect a little at the beginning, and then after that they're different. So the basic idea is what the author calls the counting principle. So just let me write down where I am here. Chapter 2, combinatorial methods. Combinatorial methods. And it starts on page 38. And the first thing he does on page 39, he talks about the counting principle and the generalized counting principle, making a big deal out of nothing. All right, so I'll just write counting principle. I'll put a S in there because he has two of them. Counting principle, generalized counting principles. This is on page 39. And the basic idea is that if I have something that can happen in one ways and something else that can happen in two ways, then the number of ways that they can happen together is n1 times n2. So for example, in the dice problem where we had two dice, and there was x1 was the value of the first die, so it could take values 1, 2, 3, 4, 5, 6. And x2 was the value of the second die, and it could take values 1, 2, 3, 4, 5, 6. Then if we considered all of the two tuples, where the first value is x1 and the second one is x2, that represents in the diagram these cross points in the grid, then if you count them, there are 36 such points, and that's obviously 6 times 6. So that's the counting principle. The generalized counting principle is the same thing except more than two dice, that's all. All right, so it makes it look more difficult than it really is. And he gives some examples. So let's start with example 2.6, which he calls the standard birthday problem. So now we're back to homework 1. So here is example 2.6. This is on page 41. And this is the birthday problem. What he calls the standard birthday problem, because as I said, there were different ways to look at it. The way we looked at it in homework 1 was we said, suppose that we question people one at a time until we get a match, and then ask the question, on average, how many people do you question until you get a match? The version that he's going to use here is slightly different. I mentioned this before. What he does is he fixes the number of people, n, and he says, what's the probability if there are n people together in a room that at least two of them have the same birthday? So that's the way I want to answer this question. Of course, they're related, and later on we'll answer we'll actually make a theoretical calculation for the average value that we got in homework 1, and you'll see it'll turn out to be very close to what you got when you ran your simulation. Okay, so the standard birthday problem, what he wants to calculate is what he calls Pn. And that is the probability that no two people have the same birthday. So this is equal to the probability of, I'll say, no match among n people. Okay, so that's what piece of n means, but that's really not the way the question was asked, because he didn't say, what's the probability that if I have n people together in a room that none of them will have the same birthday? He said, what's the probability that at least two of them will have the same birthday? In other words, what he's asking for is the event that's the complement of this. He's not saying, what's the probability that the birthdays are all different? He's saying, what's the probability that at least two people have the same birthday, which means, what's the probability that the birthdays are not all different? So therefore, what he wants to calculate is not p sub n, but 1 minus p sub n. But this is the first trick, because remember that the probability of any event is equal to 1 minus the probability of the complement of that event. So if A represents any set or event, then if I want to calculate the probability of A, I could just as well calculate the probability of its complement and subtract from 1. I do whichever is easier. So in this case, the question is to find the probability that there is a match, and to do that, I will, because it's easier, I'll calculate the probability that there is not a match and then subtract that from 1. So when I get the answer, what I want to do is I want to make this table. So here I'm going to have the value of n, the number of people in a room, and here I'm going to calculate 1 minus Pn, where Pn is the probability of no match, so 1 minus Pn is the probability that there is a match, and I want to do it for different values of n. So we'll fill that in a moment. The point now is to figure out what the probability of n is. Okay, so we want to calculate probability of no match. Okay, so now comes this combinatoric argument. So what I'm going to say is, I imagine I've got these n people in a room, and so I'm going to first define my sample space. So I'll define my sample space as a vector in which the elements are the birthdays of the people in the room. So in other words, the sample space is going to consist of points that look like this. B1, that's the number of possible birthdays for person number 1. And B2 is the number of birthdays for person number 2, and so forth. So I have n people in a room, and since there are 365 possible values that B1 could take, and there are 365 possible values that B2 could take, and so forth, the total number of vectors I can write, and each such vector would represent the birthdays of the people in the room, of the n people, would be 365 times 365 times 365, and so forth. If I consider that every possible sequence of n birthdays is equally likely, then to calculate the probability that any particular set of birthdays occur, what I do is I count how many ways that can happen divided by the total number of points in the sample space, which is the total number of these sequences or vectors. So how many is that? According to the generalized counting principle, that's 365 to the nth power. Okay, so that's the counting principle. Right? In other words, imagine that I have this room with 365 people in there, and I'm going to list every possible set of birthdays they can have. So there are 365 possible choices for the first person's birthday, 365 possible choices for the second, and so on. So if I listed every such sequence of a birthday for person 1, a birthday for person 2, and so forth, the total number of these points, these vectors in the list, would be 365 raised to the nth power. Obviously, unless n is tiny, this is a gigantic number, so you couldn't expect to actually write those things down. Now, by putting this in the denominator, I'm making the assumption that every sequence of birthdays is as likely as every other sequence. That's my model. Everything, all the points are equally likely, and this is the number of points there are. So now in the numerator, I have to count how many points there are that meet the condition, which is that when I go through this list, I'm going to list only those points in which all the birthdays are different from each other. And then, of course, I'm going to subtract that from 1 to get the probability that they're not all different from each other. Okay, so now, again, I apply the same counting principle. So I say, well, let's see. I'm going to imagine that these zillion points are listed down, and there are 365 choices for the first person's birthday. So there are 365 selections or numbers I can put in for B1. But now, once I do that, there are only 364 choices for B2 if there's to be no match, if they're to be different. So the total number of ways I can make B1 and B2 such that B1 and B2 are not equal is 365 times 364. But now once I list those, for every B1 and B2 that don't match, now I've got to put in a B3 that doesn't match either of those first two. And how many ways can I do that? Well, it would be 363. And that's it. I just multiply these things out, and the total number here would be 365 minus n plus 1. Okay, so this term is 365 minus 0. That's 365 minus 1, and so forth. And the total number of terms in the numerator is the same as number of terms in the denominator, namely n. So, for example, when n is equal to 2 people in a room, then this would be 365 minus 1 is 364, and the probability that there would be no match would be 365 times 364 over 365 times 365. The 365s cancel. It would be 364 over 365, which is exactly common sense. 2 people in a room, the probability that the second person's birthday does not match the first, 364 chances out of 365. Okay, so you just got to make sure you see that the total number of factors in the numerator and denominator is the same. And now that's it. That's the answer. That's the probability that there is no match. So 1 minus that is the probability there is a match. So it's simple. There's nothing to it. The interesting thing here is that when you plug in numerical values, the answers turn out to be different from what most people would expect. So there's really, this illustrates, I think, 2 aspects of probability theory. One is that you have to be possibly tricky in how you formulate the problem. Now, this isn't that tricky, although maybe it's tricky from the beginning if you haven't seen this before. But the first thing is a strategy. How am I going to get a formula for the probability that I want? And then the second piece is, now if I actually put numbers in that formula, is that going to give me a number that is consistent with my intuition or not? And my claim is that in a lot of cases, the answer will not be consistent with your intuition, which is an interesting fact because you've lived your whole lives, most of you, with certain beliefs about the way the world works, and now I'm going to show you that, at least in some of these cases, what you think is happening is exactly the opposite of what really is happening. Okay, so let's just plug in the numbers here. And I can calculate these numbers easily. I calculate them recursively, of course. I wouldn't calculate each one of these separately because I have gigantic numerator and denominator. I calculate the case for n is equal to 1, then for n is equal to 2 in terms of the probability for n equals 1. Because each time I increment n, I have the same thing I had before times one more term, which is a simple ratio. And we'll see that later on in the course when we do some of these calculations. Okay, so let's say you did those calculations. If n is equal to 10, the answer will turn out to be 12%. Now 12%, that's approximately 1/8. So that means that if you had only 10 people in a room, the chance is 1 out of 8 that at least 2 of them would have the same birthday. So if you have a bunch of people working in an office and they agree that they're going to go out and treat each of the others to a birthday, to a lunch, that is. The person whose birthday it is will get a free lunch paid for by the others, and there's 10 people, then it's really not surprising, because it would happen 1 time out of 8 that at least 2 of those people would happen to have exactly the same birthday. So that's really amazing. When you plug in n is equal to 20, the answer is 0.41. When you plug in 30, the answer is 0.71. 71% with only 30 people. With 40 people, maybe that's roughly what's in this room, the answer would be about 89%. With 50 people, it's 97%. With 60 people, it's 99.5%, almost certain. And this curve is going to run from 1 over 365 to 1, as I drew on the board previously, and it'll cross the 50% point at about 23. So for 23 people, if you calculate this answer, that thing right there, it's exactly 0.507, just slightly more than 50%. So at 23 people in a room, the chance is roughly 50-50 that at least 2 people will have the same birthday. Now, since the chance is roughly 50-50 at 23, if I asked you on average how many people have the question until I get a match, you would expect the answer to be roughly somewhere around 23. Not exactly, but intuitively, and that's correct. If you ran the simulation, you'll see that your answer turned out to be probably some number around 24.5, something like that. And as we'll see when we actually make the theoretical calculation, the correct answer is 24.6. So probably most people were surprised at that. Is that right? Everybody surprised? I'm surprised, and I've seen it every time, so it continues to surprise me. Okay, so that's all I want to do with Chapter 2, or with Section 2.1, excuse me. So you can read those examples, but I think the book makes it more difficult than is actually necessary. So now, once we see the basic idea, now we want to be more systematic about it, because you can't answer every question as simply as that. So now it's going to get a little bit more complicated, but the basic idea is the same. So any questions about this? All right, so I want to go to section 2.3, where he talks about what are called permutations. So this is section 2.3, which is on page 47, and it's called Permutations. And a permutation is simply an ordered arrangement. So he has a definition here, and he used this notation. Suppose I have a set of n distinct objects, and I choose R of them, and I put them in a line. I arrange them. How many different ways can I do that? And the notation is NPR. So this is the number of permutations I can make from a set of size n if I choose R of them and line them up. How many different ways can I do that? And so it's an ordered arrangement. So this thing here stands for number of ordered, as opposed to unordered, which we'll get to next, arrangements. And the answer to this is simple enough. In fact, you've already done it there. This is given by equation 2.1 in a textbook. And simply this. There are n choices for the identity of the first object, and then once I've picked it, there are n minus 1 choices for the identity of the second object, and by the principle of counting, the total number of ways I can do that is n times n minus 1, and so forth. And I'm going to do these r times, so the last term is n minus r plus 1. And in particular, for the particular case where you take all the elements of the set and arrange them, that would be npn, which is n minus 1, and so forth. And the last term would be 1. And there's a name for that, or a notation. It's usually called n factorial, which is an n with an exclamation point. That's 2.2 in the textbook. Okay, so that's simple enough. And then he has some examples of that. So here's example 310. Or 210. This is page 49. So he has 3 people, Brown, Smith, and Jones. They must be scheduled for job interviews. These are always stupid examples. But in order to make it look like it's applied instead of theoretical, instead of saying elements A1, A2, A3, he's got to name them Brown, Smith, and Jones, and he has to think of some reason. Job interviews, I don't know, standing in line, who cares? Anyhow, there's these 3 different people, Brown, Smith, and Jones. How many different orders are there? How many ways can you put them in a line? And the answer is, well, there are 3 people, so there are 3 factorial, 3 times 2 times 1, or 6 ways you can do it. And you could write it out. I mean, you could write, what are they? Well, you could have A, B, C, you could have A, C, B, you could have B, C, A, you could have C, B, A, you could have C, A, B, 1, 2, 3, 4, 5, what did I miss? BAC? Okay. So it's easy to verify that there are going to be 6 possible permutations, and you can see it's easy enough in this case. You can count and see they're all different, and you can see that nothing has been left out. Okay, but it can get more difficult than that quickly. So here is example 2.11. Here he says, suppose that 2 anthropology, 4 computer science, 3 statistics, 3 biology, and 5 music books are put on a bookshelf with a random arrangement. What is the probability that books of the same subject are together? So he's going to call that event A. So he wants to calculate the probability of A. So A is the event that when I put these books on a shelf, that the computer science books are next to each other and the anthropology books and so forth. Okay, so the first thing is, if you're going to calculate a probability, that means that you, in this case, because that's all we know at the moment, is you're going to calculate a ratio. You're going to assume that every possible arrangement of the books on the shelf is as likely as every other one. And therefore, the probability of any particular arrangement is the ratio. The denominator is the number of arrangements, and the numerator is the number of arrangements that meet the condition, which in this case is that books of the same topic are next to each other. So there are altogether 17 books which are going to be arranged. In other words, the n is 17. So the denominator is 17 factorial, which of course is a gigantic number. Okay, now in the numerator, I want to know how many different ways I can arrange these so they're all together. Let's see, these books are, what do we have? We have 2 anthropology books. So there's Anthropology 1, Anthropology 2. And then there are 4 computer science, C1, C2, C3, C4. And then there's 3 statistics, S1, S2, S3. And there are 3 biology and 5 music. B1, B2, B3, M1, M2, M3, M4, M5. So, if you count them, if I didn't make a mistake, there's 17 of these guys. That's a 17 factorial. Okay, now, I want to know how many different ways I can permute these things such that the A's are next to each other, the C's are next to each other, and so on. So first of all, I'll say, okay, how many ways can I mix up the A's? And the answer is, well, there are 2 of them, so there are 2 factorial ways I can mix up the A's. 2 factorial, of course, is 2. How many ways can I mix up the C's? Well, 4 factorial. How many ways can I mix up the S's? 3 factorial. How many ways can I mix up the B's? 3 factorial. How many ways can I mix up the M's? 5 factorial. Okay, so if I had A followed by C, then S, then B, then M, and I just looked at the number of ways I could mix up the anthropology books among themselves, the computer science books among themselves, and so forth, the probability of any particular arrangement of A, C, S, B, M would be given by that number, whatever that is, divided by that number. But I don't have to have anthropology and computer science. I could have computer science and anthropology. So now I have to multiply this by the number of different ways I can commute ACS permute ACSBM. And there are 5 different types, A's, 1, 2, 3, 4, 5. So I have to multiply this whole thing by 5 factorial. The same principle, but I'm applying it twice. So I multiply that by 5 factorial. And now I just do the arithmetic. Okay, according to the book, yes, the answer is approximately 6.996, which is about 7 times 10 to the minus 8, which I think is, for most people, a surprisingly small number. In other words, about 7 times out of 100 million, let's see, 10 to the 9 would be a trillion, right? No, 1,000 million billion. Okay. So this is about 7 times out of 100 million. Only 7 times out of 100 million. Would it be true that the books just happen to be ordered such that books of the same topic are next to each other, if that occurred at random? So if you walk into someone's office, you see all the books lined up nicely, you know it's pretty likely that there's the evidence of human hand there, that it didn't just happen at random, that the books just turned out to come out in the proper order. Okay, now we've got lots of these examples. Some of them are more difficult than others, but the difficulty is generally one of visualizing what the arrangements are and how to count. From a probability point of view, it's all, as a mathematician would say, trivial, because there's only a finite number of possibilities, and all you're doing is counting them. So it could be hard or it could be easy, but whether it is or not, that's a combinatoric problem, whether it's hard or easy. It's not a probability problem. One more thing before we go on to the next section, I think is worth mentioning. Theorem 2.4 asks a question like this. I'll just write Theorem 2.4 and give an example. And the question is, for example, suppose I had the letters Mississippi, M-I-S-S-I-S-S-I-P-P-I. And I want to permute them. I want to ask, how many different words can I make out of the letters that make up the word Mississippi? Okay, I'm going to use all the letters, but now if I imagine that they're all distinct, then the number of permutations would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there would be 11 factorial different ways I could mix up these letters, except that when I mix them up, when I interchange, for example, the 2 S's, it's the same thing. So I could envision the S's as being distinct, S1, S2, S3, and S4, let's say. But once I have those S's, when I mix them up among themselves, they'll have exactly the same word, because I don't distinguish one S from another. So when I calculated that 11 factorial, I had in here the product that corresponded to, well, let's see, there's one way I can mix up the M's among themselves, because there's only one M, but there are 4 I's, there are 4 S's, and 2 P's. So I have to factor that out, I have to divide that. So if I took this 11 factorial and divided by 1 factorial for the M, which is 1, and then 4 factorial for the I's, and then 4 factorial for the S's, and 2 factorial for the P's, then I would have the number of distinguishable arrangements of those letters. Okay, so it's the same kind of argument. This is not a probability now, this is just a counting. And notice that 1 plus 4 plus 4 plus 2 adds up to 11. Okay, so that's an example of Theorem 2.4, which in fact is one of the examples in the book. It's exercise 11, page 52. So you can see that this stuff could be tricky, but in principle, it's simple. No. Any questions about that?
This is combination, right? It's not combination.
I didn't get to combinations yet. We're on permutations. Combinations is the next topic. Okay, so permutations is simple. Combinations gets a little bit more confusing. So I'm up to section 2.4. Combinations. And this is on page 54. And he has a definition for combinations just like he has for permutations. And in fact, he defines combinations this way. That this is the notation, NCR. So I have a set of size n, and I ask how many different combinations there are of those things if I take them r at a time. And where a permutation was an ordered arrangement, a combination is an unordered arrangement. To me, that doesn't make a lot of sense, because arrangement seems to imply order. But what he's trying to do is contrast the fact that here I take these guys and put them in a row, and here it doesn't matter how they're arranged. All that matters is what they are. That is what their identities are. So he calls that an unordered arrangement, but it's really an unordered set. Okay, so he gives a formula for that, but what I want to do is I want to derive the formula first, and rather than just give it, and try and motivate it. So first thing I'm going to do is I'm going to define something else. I'm going to define this symbol. There's an N, there's an R. And in fact, it'll turn out that this and this are the same thing, and these notations are used interchangeably. Okay, so this thing I'm going to call equal to the number of ways to interleave R1s and N minus R zeros. Okay, so I have this string of zeros and ones. There are R1s, so here I got these ones. So I have R of them, and then I have N minus R zeros. So there's altogether N of these binary numbers in the string. And I want to know how many different ways I can take the zeros and ones and interleave them. So I make the following argument. First of all, imagine that these ones and these zeros are all distinct. In other words, this one is different from that one, is different from that one, and so forth. There could be like coins, and every coin has a 1 or a 0 written on it, but the coins are physically distinct from each other. So the first thing I'm going to do is ask how many different ways I could permute these n things. How many permutations or arrangements are there of those n items? And the answer, as you know, is n factorial. Now I'm going to permute them a different way. I'm going to count them a different way. First thing I'm going to do is permute the ones and ask how many ways I can mix them up among themselves. And the answer is r factorial. And then ask how many ways I can mix up the zeros among themselves. And the answer is n minus r factorial. Okay, so now I've got the total number of ways I can mix these guys up among themselves, multiplied by the total number of ways I can mix these guys up by themselves. And now I want to multiply that by the total number of ways I can then interleave them. And that, by definition, is this symbol right here. So this gives me an equation, because this counts the total number of permutations by simply mixing up all n of them. This counts the total number of permutations by mixing up the ones, mixing up the zeros, and then mixing the ones and zeros together. Okay, so this counts one way, this counts another way, so therefore by algebra, this thing, n choose r as it's called, must be equal to n factorial divided by r factorial times n minus r factorial. So in other words, if that's what I mean by the number of ways to interleave things, then that is, if I mean by unordered arrangement that, which I'll show in a minute I do, then that means that this formula is given by this, because I'm going to show that that and that are the same thing. Okay, so now I want to go back to this unordered arrangement idea, and I want to phrase the question this way. Suppose I have this set of objects, A, which is set A, which is elements A1, A2, up through AN. And what I'm going to ask is, how many different subsets of size R can I choose? Because a subset is simply an unordered arrangement. That is, I pick some out, but since they're not ordered, well, then it's a subset. So when I use the word arrangement, to me that's confusing, but I think the author does that because he wants to contrast ordered arrangements, which are permutations, with unordered arrangements, which just have to do with what the identities are and not the order in which you put them. Okay, so the way I'm going to do it is I'm going to define a subset this way. I'm going to write the elements A1, A2, and so forth, AN. And if the element is in the subset, I'm going to put a 1. And if the element is not in the subset, I'm going to put a 0. Okay, so for any string of 1s and 0s, that defines the subset. Because every element that's in the subset has a 1 under it. Every element that does not have 1 under it, has a 0 under it, is not in the subset. So every string is a subset, every subset is a string. So therefore, the question as to how many subsets there are, which is the same thing as how many unordered arrangements there are, is how many different ways can I interleave the 1s and 0s. And if the subset is to have R items in it, and there are n items in the original set, that means that what I have is I have R1s and n minus R0s, and I want to know how many ways I can interleave them. Every different interleaving gives me a subset of size R. How many such interleavings are there? Well, the number of such interleavings we just found is exactly that, which is that. So this is equal to that, which is therefore given by this formula. So what this says then, this is the way we're going to use it, is that if I have a set of n objects and I'm going to choose a subset of size R, the number of different subsets I can choose is given by that formula. So if I ask, for example, I have a deck of 52 playing cards and I want to know how many different 5-card poker hands there are, the answer would be given by 52 choose 5, whatever that turns out to be, which we'll discuss next time. Because the set, that's a set of all cards, there are 52 different cards. I'm going to choose 5 of them. I don't care what the order is, I only care what the identities are. So therefore, the number of different poker hands, so I say we'll get back to this later, is 52 choose 5. I plug into that formula, that gives me a number, it'll be about 2.5 million. And if I assume that when I shuffle the deck, every possible poker hand, every possible set of 5 cards is as likely to occur as every other one, then this would be the denominator in my probability problem. This would be the number of different possible hands that can be dealt. And the numerator would be the number of hands that have a particular characteristic, like full house or straight or something of that sort, and that's how you calculate probabilities in poker. So that'll be what we'll do next. Okay, so we're running out of time. See you on Tuesday.